When a high-speed rotor assembly is forced beyond its mechanical limits, the metal warps, vibrates, and eventually tears itself apart as shrapnel. This specific mechanical failure occurred at Natanz, a massive industrial site buried in the desert of central Iran. The facility houses thousands of IR-1 centrifuges, which must spin at constant supersonic speeds to enrich uranium. In late 2009, over 1,000 of these machines broke down in a single wave, far exceeding the plant's normal rate of equipment failure. Investigators realized these were not manufacturing defects. This was the first instance of digital code being used to trigger a large-scale physical destruction of hardware. Security at Natanz relied on an air gap, meaning the factory's control network had no physical or wireless connection to the public internet. To breach it, the attackers used a 500-kilobyte program called Stuxnet, which entered the facility on a removable USB flash drive. Stuxnet was programmed with 4 separate Windows zero-day vulnerabilities, allowing it to silently jump from the drive to any computer it touched. This diagram shows Stuxnet's peer-to-peer update mechanism. Once inside, infected computers automatically shared the latest version of the malware with one another. This allowed the software to update itself and coordinate the attack across the entire facility without ever needing an internet connection. By spreading autonomously through a closed network, Stuxnet proved that a physical disconnect from the internet was no longer a guarantee of safety. Stuxnet was designed with a high degree of restraint. It spent weeks surveilling infected networks, looking for one specific configuration. The malware hunted for computers running Step 7, a Siemens software suite used to program the logic controllers that serve as the factory's brain. It then counted exactly 33 frequency converters, the specialized power units that control motor speeds, manufactured by specific firms in Finland and Iran. If Stuxnet did not find this hyper-specific hardware layout, it remained dormant, preventing the code from being discovered on systems it wasn't meant to sabotage. Only when it confirmed the exact target did Stuxnet finally inject its own malicious instructions into the controller's memory. This level of digital fingerprinting allowed the weapon to act with the precision of a sniper, ignoring thousands of other computers until it identified its exact mark. This flowchart illustrates Stuxnet's state machine logic. For 13 days, the malware sat in a passive state, recording normal centrifuge speeds. It then transitioned to an active state, intercepting and rewriting commands sent to the drives. This graph tracks the motor's frequency. Under normal conditions, the IR-1 centrifuge rotor is kept at a stable 1064 Hz. During the attack, Stuxnet suddenly ordered the frequency to spike to 1410 Hz for 15 minutes. At this frequency, the aluminum rotor reaches a tangential speed of 443 meters per second, the exact mechanical breaking point for high-strength aluminum. After the spike, the code waited 27 days before dropping the frequency to 2 Hz, forcing the machines to slow down almost to a halt before repeating the cycle. By continuously cycling the hardware between these two extremes, the software forced the metal components to fatigue until the centrifuges shattered. Centrifuges are loud and violent when they fail. Normally, an operator would have seen the speed fluctuations and manually shut down the line. No one intervened because Stuxnet was equipped with a logic controller rootkit, the first of its kind. The rootkit sat between the hardware and the control room, intercepting the data signals that human operators relied on to see what was happening on the factory floor. While the machines were actually being destroyed, the rootkit replayed the 13 days of normal data it had recorded earlier, showing the operators a perfectly stable 1064 Hz on their screens. The operators were looking at a digital loop of a healthy factory, while the physical equipment in front of them was being reduced to scrap. Iranian officials eventually admitted that their nuclear sites had been targeted by a software attack that incapacitated a significant portion of their enrichment capacity. However, because of the way Stuxnet was programmed to spread, it eventually escaped the facility on infected drives, spreading to over 100,000 computers globally. This escape made the architecture of a kinetic cyber weapon public. Every government and non-state actor now had the blueprint for turning software into a physical strike. This logic can be adapted to target automated systems of water plants, gas pipelines, and power grids, blacking out cities from thousands of miles away. Stuxnet proved that code can be used as a kinetic weapon, leaving every piece of physical infrastructure controlled by a computer vulnerable to a software attack.